Hello everybody, my name is Rishi, and today I'll be going through solving DeepML problem number 20. The problem is decision tree learning. So the task is to write a Python function that implements the decision tree learning algorithm for classification. The function should use recursive splitting based on entropy and information gain to build a decision tree. It should take a list of examples. Each example is a dictionary of attribute value pairs and a list of attribute names as input, and return a nested dictionary representing the decision tree. Some tie-breaking rules. So if multiple attributes have equal info gain, choose the one that appears first in the attributes list. If a leaf node has equal counts of different classes, return the class that comes first alphabetically, and process attributes values in sorted order to ensure a consistent tree structure. So how we'll go about this is we will create a flowchart for this for the entire algorithm, and then after that we'll code it up. In the process of coding it up, I will also teach you more about the specifics of each part of the algorithm and what it does. This is also called the ID3 algorithm if you want to look it up. Okay, so very start, when we get the learn decision tree function, we get as input examples, attributes, and target attribute. Okay, so at the top level, what we need to do for learning a decision tree is first, we need to find attribute with the highest information gain. Find the attribute with the highest information gain. Okay. Secondly, we need to divide the dataset based on the values of the attribute with the highest information gain. So divide dataset based on values of attribute with highest info gain. Third, we need to recurse on each subset of the dataset to get the tree. So third is recursion on each subset of the dataset to get the tree. And at the end, we have to return the tree. I believe, yeah, it wants us to return tree, and then that's end. Okay. Also, need to add in the base cases. So add in a block here called base cases. If all examples have the same value for target attribute, return that. So if all examples have same, I'm just going to specify that later, actually. That would be too much to write here. So let me just space this out so it's more readable. Okay, so that's the top level on what the algorithm should do. It takes in examples, attributes, and target attribute, and then finds the one with the highest information gain, divides the dataset based on that, and recurses to find the tree furthermore. So what you can think about this is that by forming the tree based on the attribute with the highest information gain, we essentially have each choice in the tree, each node. That first node will be the attribute with the highest information gain. Second node will be the second highest information gain, and so on. So that way, each step of the tree, each way, each path that splits off for each node, always comes from a node that gives the most information gain out of every other piece of the data left in the tree. Okay, so now let's go through and flowchart each parts of these. So find the attribute with the highest information gain. Let's connect that to the start of calculate information gain function, which is up here. So what this does is, well, first let's define the formula actually. So there's a good formula for it. It's this. This is the formula for calculating information gain. So IG stands for information gain, D's dataset, A is the attribute being evaluated. DV is the subset of D for which attribute A has value V. So think of DV as being a dictionary where attribute A is the key, and the value is all the possible values that attribute A can take on. And what this is saying is we want to take H of D. H is the entropy, the Shannon entropy of the data set. Subtract the sum of the length of the data set where attribute A has value V divided by the length of the data set multiplied by the entropy of the data set for D where attribute A has value V. So it looks pretty complicated, and that's because it is, but we'll work through this in code because it's more easy to understand when we have like actual Python code going through each step of the way. So, but first thing to do is define dv. The second thing to do is calculate information gain based on this formula. And the last thing to do is to, as always, return the information gain. And then it's the end. Okay, but how do we calculate information gain? The way we do that is we need to take, as I explained above, well, I explained that above, but the way we calculate information gain is we need the Shannon entropy. So a key step in this is calculate Shannon entropy. So calculate entropy. Okay, and this is where our calculate entropy function comes into play. So how calculating entropy works. This is the definition for Shannon entropy. So simply put, it's -1 multiplied by the sum of the proportion of examples belonging to class X multiplied by log base 2 of the proportion of examples belonging to class X. Now, that may seem like a lot of words, like, P of X being the proportion of examples belonging to class X. But simply put, P of X is the probability an outcome will happen. So, for example, if we have class X and has 2 different labels, and those labels are equally represented in the dataset, then each label has 0.5 as their individual P of X values, because the probability of getting each label, if we have 2 labels that are equally represented in the dataset, is 0.5. It's a coin flip. So P of X is equal to the number of times X appears in labels divided by the length of labels. So say X is some attribute of a label, something that a value label takes on. It's that, the number of times it appears divided by the length of labels. So the first step in calculating entropy is find P of X. Second step, and this is combined step, calculate Shannon entropy and return. And last step is the end. Okay, now there is one more function here, majority class. When would we use that? Well, one of the base cases we'll use involves majority class. So then we get here, so start majority class. So one of the base cases is if there are no more attributes left in the data set that's passed in through recursion, then return the majority class. So majority class, we take in the subset of the dataset and the target attribute, And what we do for it is first we find target values of the target attribute. Okay, and second step in finding majority class is find the most frequent value. The third step is actually a step from one of the tiebreakers mentioned earlier, which is alphabetical sort. And the last step is return the label with the most frequent value and is highest in the alphabet. And by highest, I mean like, closest to A. Okay, that is the flowchart for this. So, zooming out, this is the flowchart for creating the entire algorithm. So, let's go through and let's do this one by one. Let's piece together the smaller parts to build up to the big part of the algorithm. So, let's start with calculating entropy. Okay, and this is the part of the algorithm. So, first thing to do is find p of x. Second thing to do is calculate Shannon entropy and return. So, p of x is the probability an outcome will happen. E.g., we get a label of class x. And p of x equals num times class x appears in labels divided by the length of labels. So we can define total length as length of labels because we get input of labels, and the p of x, the label probabilities is equal to a counter of the labels, which returns a dictionary. Note that we have counters imported up here, so I don't think this was in like the original problem, but I included importing default dict, and counter because they're very useful. Okay, so counter labels, that essentially creates a new dictionary where each label is a key and its value is its frequency. So now probs, or p of x, is equal to torch.tensor of the label prob divided by the total length for label probability in label probs.values. Okay, so what this does is it creates a tensor from a list, and the list is created via list comprehension, and the list comprehension is calculating p of x for each class, p of x for each class inside the data set. So the way it does this is it divides the number of times class x appears divided by the length of labels. And we can see that here, label probability divided by total length. Oh, sorry, I meant like each time a label appears, not each time a class appears, yeah. Okay, and now step 2 is calculating Shannon entropy and returning. So we can turn and look back at the formula here. It's negative of the probabilities of p of x times torch dot log 2 of the probabilities, but summed for the last dimension, and then dot item because we want to return a float. So what this does is it takes p of x times log base 2 of p of x, sums it for the last dimension, because note that the first dimension in PyTorch is always the batch dimension, or the samples. So how much we have, it's rows. And the second dimension, the last dimension, is columns, it's the features. So we sum along the last dimension, and we do dot item because we want to get a float. Okay, and that is Shannon entropy. Now, next thing to do, that ties into information gain. So let's implement calculate information gain. So a couple things to know. Information gain is equal to entropy of dataset minus sum of, well, actually, yeah, it's minus the sum of the parts of dataset, the length, where dataset is of attribute has value b. So like this, the length of dataset where attribute a is value b divided by the length of dataset times the entropy of the dataset where attribute a has value b. So that's a lot of words. So d where a has value v is dv. A is an attribute. Target attribute is what we are trying to predict. V is a value A can take. So, yeah. So the first step here is define dv. Second step is calculate info gain. Third step is return. So, when defining dv, let's say dv is equal to default dict list. So this creates a default dictionary where like adding a value to the dictionary, if the key already exists, just creates a list inside that key's values. So if we have a dictionary where, like, for example, key outcast is tied to, or no, sorry, value outcast is tied to key of yes, and value outcast is tied to key of no, then that would just end up being a value a key of outcast being tied to value yes, a key of outcast being tied to value no. Then that would be a key of outcast being tied to a list of values being yes and no. So the values get turned into a list. Okay, so for finding dv, we need to loop over every row in the dataset. For every row, x and examples, we want to append the attribute value as a key, and then the entire row as the value. So dv is the dataset where attribute a is value v. Therefore, dv is a dictionary where we take the attribute value v as a key, and then we put in the entire part of the dataset as value. So dv example attribute dot append x. This creates a dictionary of all the possible values of a mapped to the entire row, which aka is the subset of the dataset where attribute a has value v. Okay, step 2, calculating information gain. So it's this formula I showed you a while ago. So there are two parts to this. First part is the entropy of the dataset. Second part is this like massive sum formula. This second part is called conditional entropy. That is the word for it. So conditional entropy is equal to 0. Let's start it. And now let's sum it up. So for starters though, conditional entropy is the amount of uncertainty remaining in a variable being target attribute after the values of another after the values of another variable attribute are known, or value of another variable attribute is known. So we loop through each data subset in DV, because DV is a dictionary. For each value of A, it takes the subset of the data set there. So for data subset in dv.values, and we calculate we need to find the labels of target attribute within the data subset, because here's the deal. For this, we need to calculate entropy. Calculate entropy fails if we have a dictionary passed in. So we need to pass in a list, I believe, of the labels of the data. So the labels that target attribute takes on. So labels equals row target attribute for row in data subset. Okay, so labels is what we pass in to calculate entropy. We cannot pass in the data set, we have to pass in labels, which is why we do that. So now let's find entropy. So entropy equals calculate entropy of labels. Now let's find this ratio, dv divided by d, of the length of dv divided by length of d. So this is called the weighted average ratio. So weighted average ratio is equal to length of data subset divided by length of examples. And now we add all of this to conditional entropy. So conditional entropy is equal to the weighted average ratio times entropy, which matches up with this inner part of the summation. Now the summation is just for going through every data subset inside DV. So now we have conditional entropy. Now let's find information gain completely. So we need to subtract the entropy of the data set. We need to subtract conditional entropy and the entropy of the data set. So data set labels, we need this for calculate entropy. So it's equal to row target attribute for row in examples. Information gain is equal to calculate entropy of the dataset labels minus the conditional entropy. Okay, and now we just return info gain. Boom. So that's calculate entropy and calculate information gain. Now let's do majority class. So as we touched on, there are a couple steps to this. First, we have to find target values of the target attribute. Second, find the most frequent value. Third, alphabetical sort. And fourth, we return the label with the most frequent value and its highest in the alphabet. So let's go through and implement each of these. So, get target value. So we have to get the value of target attribute for each row in the data set. So target vals equals x target attribute for x in examples. And what this does, it goes through each row in the data set, x, and finds the value of target attribute. Remember, the data set is just a dictionary, like a list of dictionaries. So going through this, x is a dictionary, and then we plug in target attribute to find the value of it. Okay, now find the most frequent value. Let's create a counter. So counter equals counter target vals This maps each class to its count in a dictionary. Now let's get the max frequency of all the values for all the labels. So max equals counter.values. Max of counter.values, yeah. So this max frequency gets max frequency for all of the values of all the labels. Now, lastly, let's create a dictionary of all items with the max frequency. So we find the most frequent value, and we create a dictionary of all the items with the max frequency to do this. So max frequency items equals label for label, comma, frequency in counter.items if frequency equals max frequency. Third is alphabetical sort. So alphabetical order max frequency items equals sorted. So sorted sorts it in alphabetical order of max frequency items. And lastly, return the one that's highest in the alphabet has the most frequent value. So alphabetical order max frequency items 0. This also I think meets one of the tiebreakers, I believe. Yeah. If a leaf node has equal classes counts of different classes, return the class that comes first alphabetically. Yeah, and if multiple attributes have equal information gain, choose the one that appears first. Yeah. Okay. So that is majority class. Let me condense this so it's more readable. And now we can go to learn decision tree, which is where, like, the real stuff happens. So in learn decision tree, a couple steps. First is base cases. So if all examples have the same value for target attribute, return that value. If all examples, if there are no attributes left, if no attributes are left, return the majority class. Okay. Second, find the attribute with the highest info gain. Third, divide the dataset on the values of the selected attributes. And fourth is recurse to create the tree. And fifth is return the tree. Okay. Base cases. We need these for recursion, so let's do them. So if all examples have the same value for target attribute, return that value. So target attribute values equals a list. And our strategy will be to create a set once we get all the values. If the set is length 1, then we know they all have the same value. If it's not length 1, they have different values, because sets must not have must be unique. There must not be the duplicate values in sets. So for each row in examples, target attribute values dot append row of the target attribute. That gets the value for it. Now target attribute values, set this equal to a set of itself. If the length of target attribute values equals 1, then return the list of target attribute values 0. And this implements if multiple attributes have equal information gain, choose the one that appears first in the attributes list. Wait, no, never mind. Sorry, it doesn't. That's the Well, wait. No, Dustin, sorry. I'm being dumb. Okay, now if there are no attributes left, return the majority class. The way we check this is we see if the length of attributes is 0, then we return the majority class, passing in examples and target attribute. Okay, now, main part of the algorithm. Find the highest information gain attribute. So attribute highest info gain equals this. Highest info gain is float of negative infinity, or negative float infinity, same thing. For each attribute in attributes, attribute info gain is equal to calculate information gain for examples attribute target attribute. If attribute info gain is greater than highest info gain, then highest info gain equals attribute info gain, and attribute highest info gain equals attribute. So that finds the attribute with the highest information gain by looping through each attribute, finding the information gain, and comparing it to the previously highest one. Okay, now, divide the dataset on the values of the selected attribute. So subsets of the dataset, the default dict again with list. And let's loop over each row in examples. Subsets row of attribute highest info gain dot append row. So what this does is the subsets dict stores each value and its row or rows for the attribute with the highest info gain. The key is the attribute value. The value is the list of examples corresponding to that attribute value. Next, we recurse. So, remaining attributes. We have to create a object of remaining attributes that essentially is every attribute except for the one that we've taken that has the highest information gain, because we can't repeat an attribute, so we have to remove the one with the highest information gain from the attributes list after we select it. So remaining attributes equals every attribute until attributes.index of attribute with the highest information gain plus attributes of the attributes index of the one with the highest information gain plus 1, and then to the end. So what this does is it splits and only takes every attribute except for the one with the highest information gain. And there might be a syntax error. I think that's correct, though. Yeah, okay. Now, actual recursion. Because that previously was just tracking remaining attributes. So, tree is equal to dictionary, of course. We could return a dictionary. And for attribute, value, and subset in subsets to items, tree of the attribute value equals learn decision tree of the subset remaining attributes and target attribute. So this creates the decision tree for each subset inside the subsets dictionary created above. Subsets is the data set divided on the values of the attribute with the highest information gain. Now we need to return it. We return the attribute with the highest information gain then tree. The reason we do this is because attribute with highest information gain is not included inside the tree, so we have to include it ourselves with inside the return function, inside the return. Okay, that's it. That's a lot of code. Let's hope this works. Probably a syntax error somewhere. Yeah, syntax error. Collections.defaultDict object has no attribute in line 131. Oh, it's .items with an S. Okay, and we passed the test cases. So yeah, it's a pretty complicated algorithm, so I'd recommend watching some videos online on the intuition behind it. It's a very greedy algorithm. It takes the best attribute possible, always. And yeah, this is my implementation. The code is in the description below. So yeah, hope you enjoyed. Thank you. See you tomorrow.